Good day, folks. First of all, like my apologies. The last video that was uploaded did not have sound. If there was some issue with the mic or something, so hopefully this video should work better, and you should be able to hear my voice. Welcome to this presentation on descriptive analytics for the course PMGT2851, your project analytic course. In today's session, we will explore one of the most fundamental concepts in data analytics, which is obviously the descriptive analytics. As organizations increasingly rely on data to make decisions, understanding how to interpret and summarize data has become a critical skill for project manager, analyst, and business professionals. Descriptive analytics is essential because the starting point of any analytics is descriptive because it's looking at the historical data. Before organization can predict any future outcomes or recommendation about optimal decisions, they must first understand what has already occurred. This is where descriptive analytics becomes extremely valuable. It helps organization transform raw data into meaningful insight that support organization better decision-making abilities. In this presentation, we will discuss what descriptive analytics is, why is it important, and how it is used in real business environments. We will also examine different types of the statistical measure used in descriptive analytics and help us summarize and interpret data differently and effectively. Throughout this presentation, we will look at four key statistical concepts in descriptive analytics, and these measures will help organization and obviously you guys to analyze large volume of data and communicate insights through dashboard, reports, and visualizations. By the end of this presentation, you should have a clear understanding of how descriptive analytics works, and let's get on to the class. Okay, before we dive deeper into the descriptive analytics, it is useful to understand where this topic fits. Project analytics is a discipline that focuses on using data to support project planning, monitoring, evaluation, and decision making. Modern projects generate enormous amount of data and ranging from cost, schedule, information to risk indicators, and obviously stakeholders feedback. Analytics techniques help project managers transform this data into actionable insights. Typically, project analytics can be divided into several stages. The first one is your descriptive analytics. And obviously, we'll go through diagnostic analysis on week 5, and week 7 and week 8, we'll do the data visualization, predictive analytics, and we'll do the prescriptive analytics in week 9. And okay, what is descriptive analytics? Descriptive analytics is the simplest and most commonly used form of data analysis in business today. At its core, descriptive analytics answers the question, what happened? It focuses on summarizing historical data so that organizations can rely or clearly understand the past events, current performance. Rather than predicting the future, descriptive analytics looks at existing data set and useful statistical techniques to summarize them in a meaningful way. This often involves calculating averages, percentage, frequencies, and variations within the data set. In many organizations, descriptive analytics is presented through dashboards, reports, and data visualization. These tools allow managers to quickly interpret large data set and monitor key performance indicators, commonly known as KPIs. KPIs is key performance indicators of measurable values that demonstrate how effectively an organization is achieving its objectives. For example, look at a company may track metrics such as its revenue growth or project completion rate, customer satisfaction score, or operational efficiency as indicators. Descriptive analytics helps organizations monitor these KPIs by summarizing large amounts of operational data into easily understandable format. There are many practical applications of descriptive analytics in business. For instance, organization may use generative monthly revenue report, or analyze their sales performance, or monitor customers' engagement and evaluate operational productivity. So for project managers specifically, descriptive analytics helps track their project progress, identify performance trends, and evaluate whether projects are meeting its cost, schedule, and quality objectives. Although descriptive analytics does not explain why something happened or predict future, it provides the foundation for deeper analytical insights. Look at the example of descriptive analytics. To better understand, let us look some common examples of how organizations use it in real world situations. One of the most common use of descriptive analytics is summarizing the past business events. For example, companies regularly analyze historical sales data to understand how products performed over a specific period of time. By reviewing this data, organizations can identify seasonal trends, peak sales periods, or declining product demand. Another example involves analyzing market or marketing campaigns. Companies often collect data on campaigning performance, such as website visit, advertisement clicks, and conversion rate. And even in Facebook and Instagram, if you guys using it, how much comments you have made for this particular thing. So those kind of historical data is what data descriptive analytics will look at. Descriptive analytics technique will help summarize this information so managers can evaluate how effective their strategies could be. Descriptive analysis is also widely used in social media analysis, as I just said. Organizations track engagement metrics like likes, share, comments, and followers across platforms like Instagram and Facebook. By summarizing these metrics, business can understand the customer or the audience behavior and measure the success of their online presence. So these examples demonstrate how descriptive analytics helps organizations transform raw data into meaningful insight. While it may appear simple, this type of analysis provides essential information for monitoring performance and supporting strategic decision making. Like any analytical method, the descriptive analytics has both advantage and limitations. One of the major advantages, it is simple and accessible. Because descriptive analytics relies on historical data and relatively simple calculation, it can be implemented easily in most organizations. It does not require any high advanced analytical expertise or complex algorithms, which you'll be using in AI or machine learning. This makes descriptive analytics particularly useful for daily operational reporting. Managers can quickly generate performance reports and monitor key metrics without requiring specialized data science knowledge. Another advantage is that descriptive analytics provide clear and easy to interpret insights. By summarizing data through average percentage charts. An organization can quickly understand performance trends and identify any areas for improvement. The most important limitation is it focuses on historical data, so it only tells us what has happened, but it cannot predict what could happen or what we need to change. That will be following other three analytical techniques. However, it does not automatically explain whether the decline caused by marketing campaign or pricing changes or customer preference. To answer this deeper question, organization must use more advanced analytics like your diagnostic, predictive, and prescriptive. So therefore, descriptive should be viewed as the first step in any analytical process, providing foundation for more sophisticated methods. Well, now let's look at the types of descriptive analytics. There are four major types of analytics measure which can be used to summarize and interpret data. The first type is measure of frequency, which describes how often certain values or events occurs in a data set. The second type is measures of central tendency, which identify the central or typical value within a data set. So these are basically your mean, median, and mode, which are locating at the center of the data set. So these measures help us to understand the average behavior of the data. So the third type is the measures of dispersion or variation, which describes how spread out the data values are. If you look at normal distribution, you know how your data has been spread out. These measures indicate whether the data values are clustered closely around an average or widely distributed. And finally, the fourth type is your measures of position, which helps us understand how individual value compare to other values within the data set. Together, these four categories provide a comprehensive framework for analyzing the data. So they allow analysts to summarize large data set, identify patterns, and communicate insights effectively through chart, reports, and dashboards. So in the next slides, we will explore each of these types in more detail, beginning with the measure of frequency. Okay, the first type is the measure of frequency, which describes how often a particular value or event occurs in a data set. The most common frequency measures include counts, percentage, and frequency distributions. A count simply tells us how many times a specific event has occurred. For example, a project manager may count number of project tasks that exceeded their budget. And percentage obviously represent the portion of the particular value relative to the total data sets. For example, an organization might calculate percentage of employees who are due to their annual performance review. For frequency measures are extremely useful when analyzing categorical data such as survey response, customer feedbacks, and clarification data. For instance, if a company conducts a customer satisfaction survey, frequency analysis can show how many customers rated the service as excellent, good, average, or poor. In project management context, frequency analysis may also be used to track project risk, schedule delays, and resource allocation pattern. Overall, measures of frequency provide a simple yet powerful way to understand how often certain outcomes occur within a data set. So the second type is your measure of central tendency. As I said before, it's about your central the value of the data set. And it helps us to identify the central or typical value in a data set. The three most common measures of a central tendency are mean, median, and mode. The mean, often called as average, is calculated by adding value in a data set and dividing the total by number of observations. So the median represents the middle value when all observations are arranged in order from smallest to largest, or vice versa. The mode is the value that occurs most frequently within the data set. Each of these measures provide a slightly different perspective on data. The mean is widely used because it considers all data values in the calculation. However, it can sometimes be influenced by extreme values or outliers. The median is particularly useful when data are skewed because it is less affected by extreme values. And finally, the mode is useful for identifying the most common category or value in a data set. Another variation is we call it weighted mean, which assigns different levels of importance or weights for different data value. So if you look at calculating your quiz and exams, so probably, for example, we'll say your quiz is weighted for 20% of your total mark and your final exam is 80%. So if you score 80 in your quiz and 90 in your final exam, we'll take 20% of that 80 and then 90% of 80% of that 90, which gives you the weighted. If you add both, it will give you the weighted value. That's what weighted mean. Measures of central tendency are fundamental tools in descriptive analytics because they summarize large set of data set into a single representation value. So let's look at the mean of a discrete probability distribution. So far we have seen the average, which gives you, you add all the values and divide by the number of observation. But there's also a concept called mean of discrete probability distribution. In some cases, all those mean value, average value cannot be giving you the insight that you are looking at. In the case of some unexpected or uncertain situation, you need to have an expected value. So we'll talk about that. In this slide, we introduce the concept of mean of discrete probability distribution. This concept is an important extension of the idea of an average that we commonly use in descriptive statistics. A descriptive probability distribution describes situations where a variable can take only a limited number of possible values. These values are usually associated with specific probabilities. Example could include your survey response on a Likert scale, the number of defective items in a branch, or the number of tasks completed in project during a given period in time. So to calculate the mean of discrete probability distribution, we do not simply average the numbers. I'll explain you in detail with the example in the next slide. Instead, we calculate what is known or as we call it expected value, which represent the long run average outcome of a random variable, which is given in your formula. It's mu equals sum of x. X is your possible value and the probability of that x possible value occurring. So this formula tells us that we multiply each possible value of the variable represented by x by its corresponding probability, and then sum all of these products. In this formula, x represents possible value of the variable and px obviously the probability of that value occurring. So the probability are typically calculated as frequency divided by the total number of observations. To illustrate this, imagine a project manager analyzing a number of project delays occurring each month. Suppose the data shows that 0 delays occur in a probability of 0.3, 1 delay occurs with a probability of 0.4, and 2 delays occur with the probability of 0.3. To calculate the expected number of delays, each value is multiplied by its probability and then summed together. So that's how therefore, the mean of this discrete probability helps decision makers to understand what outcome they should expect on average when uncertainty is involved. While the mean tells us average expected value, it does not tell us how spread our data values are. So to understand the variability in data, we use variance and standard deviation. I will cover variance and standard deviations in the following slides. But next, in this slide, I want you to give you some example of how mean of discrete variable, discrete probability distributions can be done. So you're looking at the realistic example or example we have given here of how and why we calculate the probability mean, and it's different from average mean. So we look at how to calculate the mean, the variance, and the standard deviation using probability. And I know a couple of students did have questions on why we don't use the simple average, which makes much easier, right? Even though it may look much easier and simpler at first. Let's begin with the scenario shown on this slide first. A project manager sent out a survey of 50 stakeholders. Each stakeholder gave a satisfaction score ranging from 1 to 5, where 1 means extremely dissatisfied and 5 means extremely satisfied. This is like a Likert chart. The total responses for each score were 8 people gave a score of 1, 11 people gave a score of 2, 14 people gave a score of 3, 10 people gave score of 4, and 7 people gave score of 5. Now, instead of calculating the simple average straight away, we convert this frequency into probability, likelihood of an event, of that event occurring. So each probability is just because it's uncertain. People can give, it's a changing thing. It's not it's not a common thing, or it is an uncertain value. Each probability is just the frequency divided by total number of response, which is 50. So for example, the probability of getting a score of 1 is 8 divided by 50, which is 0.16. We do the same for all other scores. Once we have probabilities, we can compute the mean of discrete probability using the formula mu equals sum of x, probability of that x. And when we do that for this data set, we get mean value of 2.94. Next, we compute the variance. Variance tells us how spread out the scores are around the mean. So we calculate using the mu square. And once we plug in the number, we get a variance value is 1.6. And then taking square root will obviously give you a standard deviation of 1.26. Now, let's talk about something really important. Why didn't we use a simple average? Well, wouldn't that be much easier? Well, in this case, the simple average would actually give you same numerical result, which is 2.9, because the sample is small and clean. But the real reason we use probability method is that probability means something different for average of a specific data set. A simple average only describes what happened in this one survey. But the mean of discrete probability describes what we call a random variable, which can be theoretical or might represent long-run behavior, or could describe situation where you don't have a full data set. Let me give you another example. Imagine you have a loaded die, you or slightly unfair die, and you know the probability of each phase coming up. Maybe phase 1 comes up 10% of the time, phase 2 15% of time, and so on. It's all your guess. Even before we roll the die a single time, you can calculate the expected value of that occurring, or a long run average outcome. You cannot take a simple average because you don't have the result yet, right? So, but you can calculate the mean using probabilities of that number occurring in that die. So this is exactly why we learn the probability-based mean. It is not just analyzing the past data, it is predicting and understanding the future outcomes. So to summarize, the simple average describes the data set you already have. The probability means describes the general behavior of a random variable even when you don't have real data set. And the expected value gives us a way to model and predict outcomes in the long run. That's the heart of what today's slide is showing. Now, just how to calculate the number, but why the probability approach matters. Hopefully that helps you guys. But if you have more questions on this, I'm more than happy to help you in the class. Modern analytics often relies on software tools to perform statistical calculation effectively. One of the most widely used tools we have in the market is the Microsoft Excel. Excel provides built-in function that allows users to easily calculate measures of tendency, including your mean, median, and mode. To perform descriptive analytics in Excel, all you have to do is to download, which you already seen in the class, Data Analytics Tool Pack. This tools obviously provides a simple way of generating statistical summary without performing any manual calculations. So the process typically begins by selecting the data tab in Excel on the top, then choosing the data analysis option. Within this menu, users can select descriptive statistics, your step 2, which is shown in the screen, which allows Excel to automatically compute measures such as mean, median, mode, standard deviation, variance, skewness, kurtosis, and range, maximum and minimum value, and sum. So in addition to these numerical statistics, Excel can also generate visualizations such as histograms. A histogram is nothing but a graphical representation of the data distribution, just like your normal distribution or asymmetrical distributions, things like that. It groups data values into intervals and shows how frequently value occurs within each interval. Histograms are particularly useful for identifying patterns such as normal distributions, skewed distributions, or outliers. In project analysis, Excel-based descriptive statistics are often used to analyze project performance metrics such as the task, activities, completion time, budget spending, resource allocation, and risk occurrence frequency. Now let's look at the measure of dispersion or variation. Um, Measure of dispersion helps analysts determine whether data values are clustered closely around the mean or distributed across a wide range. One of the simplest measures of dispersion is called the range. The range is calculated by subtracting lowest value in the dataset from the highest value. Although range provides a quick estimate of spread, it only considers two data points and often does not reflect the overall distribution of the dataset. A more comprehensive measure of dispersion is called variance, which calculates the average squared difference between each value and the mean. The square root of variance gives you the standard deviation, which provides a more interpretable measure of spread. When the standard deviation is small, it indicates that the data values are close to the mean and therefore relatively consistent. When the data or the standard deviation is more high, it suggests that the data value are widely dispersed. Understanding this dispersion is essential in many business and project management contexts. For example, project managers often analyze the variation in task completion or cost estimate. High variation may indicate uncertainty, inconsistent in performance, and unreliable forecast. Therefore, measures of dispersion provide deeper insight into the stability and reliability of data. What you're looking now is called the empirical value, which can also be called sometimes as 68, 95, 99.7 rules, which describes how data is distributed in a normal distribution, also known as a bell-shaped curve. In a normal distribution, data values tend to cluster around the mean, and the frequency of values determines as we move further away from mean. Mean is your center. The empirical rule states that approximately 68% of the data falls within one standard deviation of the mean, and around 95% of the data falls within two standard deviation of the mean, and the 99.7% of data falls within three standard deviation of mean. This rule helps analysts quickly understand how unusual or extreme a particular value might be. For example, if a project manager observes a project cost that falls more than 3 standard deviation above the mean, it may indicate any unusual event, potential issue, or requiring some further investigation. The empirical rule is widely used in quality control, risk analysis, and performance monitoring. It allows analysts to detect anomalies and identify patterns in large data sets. In project analytics, it can help identify tasks or activities that significantly deviate from expected performance. Understanding the empirical rule, therefore, provides a powerful way to interpret variability in normal distribution data. The fourth and the final one is your measure of position, which helps us to understand how individual value compare to other values within a data set. So two commonly used measure of position, or I think there's three commonly used measure of position is your percentile, quartiles, and deciles. But we'll focus on quartiles in this class. A quartile divides a data set into 4 equal parts. Percentage will be with 1%, 2%, and you can go up to 100%. Decile is called it divides data set in 10 value 10, 10, 10, 10 up to 100. So in quartile, it divides a data set into 4 equal parts. The first quartile represents the lowest 25% of value. The second quartile corresponds to the median, and the third quartile represents the top 75% of the value. So these measures are often visualized using a box whisker plot, also known as box plot. A box plot displays the median, quartiles, and potential outliers within a data set. Measures of positions are especially useful when comparing performance relative to a benchmark or standard. For example, organizations may compare employee performance, student test score, or project completion times relative to industry benchmarks. In project analytics, percentiles, quartiles, deciles can help identify top performing projects or highlight projects that require improvement. So obviously you're looking at the most appropriate measure of location depends on the shape of data distribution. You have symmetry, you have left skewed and right skewed. We'll explain further in the next one. So when analyzing the data, it is important to choose most appropriate measure of location such as mean, median or mode. The choice depends largely on the shape of distribution. If it's a symmetrical, which is your normal distribution, meaning the distribution is evenly balanced around the center, the mean, median, mode will be approximately equal. In this case, the mean is usually an appropriate measure of central tendency. However, if the data are skewed, meaning the distribution is asymmetrical or is stretched more on one side than the other side, the mean can be influenced by extreme values or outliers. In such cases, the median often provides a better representation of central value because it is less sensitive to extreme values. If the data are multimodal, you see the second example, meaning there are multiple peaks in distribution, it may be useful to report the mean, median, and mode for each subgroup. Understanding the shape of distribution helps select the most appropriate statistical measure and avoid misleading conclusions. This is particularly important in business analytics because incorrect interpretation of average can lead to poor decision making. And how do we interpret? When interpreting data distribution, analysts often examine whether the data is highly skewed, moderately skewed, or approximately asymmetrical, which is your normal distribution. A highly skewed distribution occurs when large number of observations are concentrated on one side of distribution, while a few extreme values extend the distribution in one side. A moderately skewed shows some imbalance, but the data is still relatively concentrated around the center. An approximately symmetrical distribution is one in which left and right side distribution mirror each other. Understanding these patterns helps to interpret the descriptive statistics more accurately. And the final one is the kurtosis. Kurtosis is a statistical measure that describes the shape of distribution, particularly how heavy or light the tail of the curve or compared to normal distribution. Put it in simpler terms, it tells us how prone a data set is to produce extreme values, which is your outliers. While many people think kurtosis measures peakness, in modern statistics it is mainly interpreted as tail heaviness. A normal distribution, which is your bell curve, is used as a reference point when interpreting kurtosis. So what is excess kurtosis? Excess kurtosis compares the kurtosis of a distribution with that of a normal. Excess kurtosis equals kurtosis minus 3. The normal distribution has a kurtosis of 3, so it is excess kurtosis is 0. So the excess kurtosis helps us understand whether a data set has more or fewer extreme value than a normal distribution. So if you look at the first one, excess kurtosis equals 0, which can also be called as mesokurtosis distribution. When excess kurtosis equals 0, the distribution behaves similar to a normal distribution. So if you look at an example, many natural phenomena such as human height, standardization, test score often approximate this distribution. And if you look at the excess kurtosis greater than 0, which we call it leptokurtic, what does it characterize? Heavier tail, often a sharper peak around this mean. This means the data set has highly probability of extreme observation compared with your normal distribution. And the last one is the excess kurtosis less than 0, which is called platykurtic. It is called lighter tail, fewer extreme values, and flatter peak. What does it mean? This means observations are more evenly spread out and extreme values are less common than in normal distribution. So other than that, we have positive kurtosis, which occurs when kurtosis is greater than 0 and high probability of outlier in that. What is the meaning of it? Data points are concentrated near to the mean, but there are more extreme observation. And there's called normal kurtosis, which is your normal distribution as excess kurtosis equal to 0. And then the last one is your negative kurtosis, where excessive kurtosis is less than 0, which means flatter peak and thin line or thin tails and fewer extreme values. Alrighty, with that, this concludes the discussion on descriptive statistical measure used in project analytics. In this presentation, we explored several key concepts, including the measure of frequency, measure of central tendency, mean of discrete probability distribution. We did the measure of discrete or dispersion of variation, which we talked about range, variance, standard deviation, and then we went on to measure of position. These statistical tools form the foundation of descriptive analysis. Understanding this concept is very important and analysts like you, because they provide insight into patterns, variability, and performance trends within the data. By applying these methods, organization can transform raw project data into meaningful information that supports your informed decision making. Thank you for your attention, guys, and I sincerely apologize again for the hiccup last time. I hope this presentation has provided a clear understanding of how the statistical measures, especially on descriptive analytics, are used in project analysis. Hopefully, I'll see you in the next class. Have a good time.